evening, everyone. So now we are going to start with the hands-on session of today's. Dr. Muqaddar Ali sir has joined us. He has completed his PhD from MNIT Jaipur, and right now more than 4 years of experience of teaching and research the sir is having. The sir is expert in the field of antenna designing, millimeter wave, 5G, SIW, and the recent trends and of antenna designing. Today, in today's hands-on session, the sir will teach the hands-on on the HFSS software. Over to you, sir, and thank you for joining, sir.
Thank you, Swati, for the opportunity. I think I am audible now. So, in this session, we are going to start our and so the ANSYS HFSS. So, let me share my screen. Okay, so for today's session, we are going to start our demonstration in student version of ANSYS HFSS. And as for the research purpose in academics, the student version is sufficient, and we don't have to go for any unethical practices for downloading the software. So, how you can download the student version? You just go through the ansys.com, and here you will be finding the student and academics section. When you click here, slide down, and here you will be able to see this free student software. Okay? So when we click here, and then it will present a list of software that are available for the students, and we are interested in antenna design, so we will be using ANSYS electronics desktop student version. Okay. So when you click here, you will be asked to register, and let us click on the download section. So whenever you are going to download this version, you will be getting a 1 year license for the software, and that license will be inbuilt. So you don't have to give any license file here. Okay, so I have already downloaded it, and so when you download it, it will come as a zip folder. So this you can extract, and I have already extracted and installed this software. So, so this is the software. Now, what you need to do, you need to double click on this setup. Once you click on the setup, it will start the process, and you just have to click next. Once the setup get started, like this. So here you can see that these are the terms of license, and most of the time we don't read these, but it is a must for reading. So what you can do, you can just copy this whole license terms and go to ChatGPT or Gemini, whatever you prefer, and ask it to help me identify the limitations of my software license. Okay, so this is the prompt that we are going to write here, and we just pasted all license agreement. So it will briefly summarize what are the limitations, and basically in student version, we cannot right now the ANSYS has implemented an anti-piracy technology in which if you are using a pirated software and you are connected with the internet, ANSYS will automatically detect your MAC address of your system and they can sue you. Okay. And there are many more ethical concerns regarding this. And if you are downloading a pirated version, then they also open some backdoors in your system for hacking. So it is best that you should be preferring a official version. And as I earlier told you that the, for academic research, the student version is sufficient. Otherwise, you can ask your institute to take the registration, take an official license, academic license that will it be sufficient. Okay. So now you have to click on this. I agree with this terms and conditions and click next. Then you will be asked if you are already not signed in, then it will be asked you to sign in. Otherwise, it will give you an option to change the directory of installation. Then click next, and okay. So it will complete. Once it completes, so you will be able to run the software. So right now I am aborting this installation because I have already installed it. Okay. So okay, so once you install it, you will be able to see this icon, ANSYS Electronic Desktop Student version on your desktop. Otherwise, you can check it in Start symbol. So once you open this, it will first time it will take some time, and it will ask you if you want to participate in the ANSYS improvement program. That is nothing but if you are your software is crashing, then they will collect some log information that for which reason it is crashing, and if you prefer no, I am not willing, then it is also fine. Okay. Then it will open. The first time it opens, the layout of the this will be like this. So sorry, uh, just please. Okay. So when you first time open, the layout will be something like this. And right now we don't see any more options, and most of these options are uh, disabled. So first we click on file and click on a new. Then it will ask us to create a new project. So right now it has created a new project, and now you see these symbols, they were disabled earlier. Now they are active. Okay. Then uh, there, it has a very similar interface like any other software. These are the file menus. We have new, open, and open examples. It has some inbuilt examples that we will explore in next session. But today we are not going to open any example files here. Then we have save and save as. Uh, these are the similar meaning. Then we can close the project by this window, and we can save a different version of for each project. Then we have copy, cut, copy, paste. These are the basic commands. Now, the important thing, this menu is an important part. In this, there are in ANSYS is basically a collection of different type of to solve different type of problem. For our purpose, we are going to use high frequency surface simulator, that is HFSS. So we click on this. So it will insert an HFSS design in our project. So our project name is project 2, and we click here. So once we click, we can see that in this project, we have this design. Now, when we click on this project, then the menu has changed suddenly. So it is desktop. This is your main window, and these options we will explore later. Okay. Now, these are the tab windows that you see in Microsoft Office or any other software. So all these have different functionalities that are categorized. Then in the layout of this interface, we see there is a project manager. So in project manager, we will be having our different simulation files that we will be generating that will be arranged here. And the, this window is our canvas in which we design our systems. And this component library, right now we will not be using it. So just close it. Then we have this canvas in which we are going to design our uh, antennas or any other devices that we are interested. And it has three major components here. Uh, the first one is a coordinate system. It is a global coordinate system, and then there are some 2D planes. So in global coordinate system, we have X, Y, and Z. So you can see this gizmo here. So red axis is X, green axis is Y, and blue axis is Z panel. Okay. So these are the three axes, and we are currently in the global mode. So this is our global coordinate system. Now, in the view tab, we see this is the save and cut copy paste. These are basically. Then in docking window, we can just right now we were able to see this component library. In docking window, we have this checklist that shows that which window we are going to display. So let we can disable this component library from here. Then in locking window, there is status bar. Status bar is here. So we can also remove that status bar. So by this, you can manage your layout. And this window is properties in which whatever objects you are going to create, it will have some properties associated with this that object, and those properties will be displayed here. Now, these two bars that are message manager and project progress. So these are when we start our simulation, we will be able to see the progress of the simulation here. And here, if we ran into some errors or some warnings are there, then it will display messages here. If even if our simulation successfully run, the message will be displayed here. Okay. Now, uh, in let us explore this project manager. In project manager, for each project, we can have multiple design files, and if we click on this plus sign, it will open our project. So here we see that it has a 3D component, then it has a model, circuit element, boundaries. All these we have to go through and check out during our design. Okay. So uh, now let us explore the next option, that is these view fields. Here, if we have multiple objects, then we can select this I button, and it will open and display a list of objects that are available in the scene. And we can select which of to choose to be visible, and which we can hide. Okay. Then we have zoom in and zoom out facilities here. We can also use the pen to move this whole structure like this. Then we can rotate like this. We can rotate around an axis particularly, or we can rotate with a freehand cursor. So all these. Then we can change the orientation. We can have different type of views: top, bottom, right, left, front, back. So let us reset to isometric view. And after going to isometric view, we see here this there are two options: fit all and fit selected. So right now, let us click on fit all option. So the fit all option reset the reset the whole canvas, and put all the elements fit inside this window. Okay. Then clipping pen. These are some pen that we will like explore later. Now, in the in next tab, that is draw tab. Here, these are the basic elements, and these we have discussed already. These are the view and zoom options. Now, these are the next buttons that we are going to discuss. So, this first we see it is a box here. It is a parallelogram. So if we select this, now it is disabled. These buttons are disabled, and you see here it is showing a measure data, and reference coordinate system is global. Position one, that is our reference position, it is displaying 00, and the second position, that is our current position. So the current position is like this. Okay. So click on any point here. So this is your first position, and it has become as a reference. Then if we move, it is moving in a 2 dimension. Okay. So basically we are creating a face of an box. Okay. Once we click again, then that second position is finalized. And now if we move the cursor, you see this has created a 3-dimensional box. Okay. So initially we select like this, we can create an object here. So let us Control Z and again create from select the box button. You need to select the first corner of your 3D object. Okay, so here we are creating a brick. So we select the first point of the brick that will start from here at this point. Now I want this brick to be rectangular like this. So it has this way. So now I click on here, then it selected the second corner. So here we are selecting the diagonals. If you see again the first corner, then we are moving and it is opposite. It is the diagonally opposite corner. So we need to give two corners that are diagonally opposite here. Once we select that corner, that has finalized. Now it is increasing in Z. You can see in the measurement data also the Z value is increasing. Okay. Now, once this Z value, we have roughly finalized the design geometry. Now, it has come in this model. We see it has created a new section that is models, and in that model, we have a subsection that is solids. Solids are basically 3D shapes. Then in solids, we have a vacuum, and then this is our box one. Okay. So let us give this box a name. So when we double click on this, it has opened its properties, and these properties are same as here. Okay. So if we click on this object, these properties can be seen here, or we can double click. Let's double click and give this as a brown. And then the second option is material. In material, when we select, then we see only vacuum is there. So we click on edit button here. Once we click on edit, it will open a pop-up window in which we can select a number of materials that are already available. This is a material library, and here we can select our material. So first we are designing a ground plane. So the ground plane will have will be of copper mostly. So let's select a copper. So it has this material property copper, and the name of material is copper. It is located in system library, and its relative permittivity is 1, relative permeability is this. These are the electromagnetic properties, relative permittivity, permeability, conductivity, dielectric loss tangent, magnetic loss tangent. All these parameters, it has a library of different material and their characteristics. So now click on OK. Then we have this solve inside. That means whenever we are creating a 3D object, whether we want to solve the Maxwell equations on the surface or inside the surface also. So we can keep it as a on. Then currently it is oriented in a global coordinate system, and it is a part of a model. Okay. Then if you want to display the wireframe diagram, then you can check on this, otherwise there is no need. Then there is a color. So color we can give of your choice. According to your choice, you can define the color. So mostly I prefer yellow for the copper element so that visually I can identify it. Then we can also change the transparency of this, but that will make this object transparent. But for now, I am not changing that. So transparency is 0. That means this object is completely opaque. Then we can set any of these property as read only, so that by accident we cannot change that in future. Okay. So first, this was the basic property. So you can see right now it is a yellow box, and if for whatever object we are selecting, the color will be in like this. That is magenta. Okay, so this represent that this particular object is selected in the hierarchy. So we have set these properties here. Now, as this was a box, so the box has certain more properties. Those properties we can set here. When we double click, so it is saying that this object was created by using the command create box, and the box is created by starting its starting position and size in all three dimensions: x size, y size, and z size. Okay, so whenever we are creating some object, we should avoid using the exact values. Like here, it is minus 1 mm, minus 0.6 mm. These are the exact values. So we should avoid using exact values. Instead, we should be using some variables. So variable are that we can change later on, and we don't have to go to if I keep here, and I want this box to I want to increase the length of this box. So I will have to go here, double click on the property, and check out in the x-axis. I want it to be 10 mm. Click OK, and then select fit all. So here we are able to see that the size is increased. But every time whenever I need to change this, I will have to come at this position. Okay. So I want to avoid that. So what I will be doing, I double click here. Then first of all, I want to create a rectangular box. Okay. So I want the rectangular box to have as width of W and length L. So I give it minus W by 2 minus L by 2, and in Z axis I am keeping it 0. So it will be a symmetric along the origin. Let's just keep the symmetry in one center only. Okay. So when I click outside, it is started asking me what is the value of this variable that I have selected. So this is very important because if I click here, that W is 1 mm. Okay. And I currently I am clicking OK, and it is an intentional mistake that I am doing. And okay. Now I click this X size is W and click apply. Okay. So you can see that it has created a very long strip, and if I click on fit all, it can be seen that it is a very long strip with a very narrow width. Okay. And now you see this X here, it is 1. And so what is happening with that, when I was designing this variable, I did not give it a dimension. Okay. So let us set the width length of this as L. Now again, so now in L it is giving a dimension. It is already selecting this unit type as length, but here it was not selecting. So the reason was uh, here I deleted this. Now select L, comma 0. So here the mm is not there, so it is considered it is not able to identify what kind of variable is this. So we have to select this variable type as length. The unit of this variable is mm, and let me give this as 40 mm. Okay. Now you see the position is minus w by 2, that is minus 0.5, and it has no unit. And L, it is 40 mm. So it has a unit, and let me set it minus L by 2. Okay. Width. So this width strip is like, so width, uh, the value of W, I wanted it in mm, but it is not there. So what we can do, X is 40 mm, and enter. So now the unit is being added here. Okay. So now if we click on fit all, so we can see that this is the box that we have created. It has a very thin in height, and the width is 40 mm, length is 40 mm. Okay. Now what we need to do, just select this box and create a copy of this. Now when selected, Control C and Control V, these are our favorite commands. So we copy this, and now we have two objects, but they are overlapping to each other. If we click on the characteristic, these are the exact same. Now I want it to overlap, do not overlap. So what we can do, we can increase the Z axis size, and for example, we have this sheet. This is the sheet that was there. Uh, that is of copper. This is your copper sheet. Now we want to add one more layer here, and we want to make it like this. Okay. So how do we place this object on this? We can this reference point where z is 0, and at this point the z is e. So we give the starting point here as t, and we want the substrate to have the same width and length. So thickness of our substrate, and let us give this as edge substrate, edge sub. So these are the variables, you can name it according to your suitability. And I'm giving it h sub, that means height of the substrate. And when I click apply, it is again asking that what is h sub. So I have to tell it that h sub is a dimension in length, and the typical value of this h sub is 1.524 m. Okay. So when I click this, now apply. So here these two objects are there, but they are in same color. So double click here, rename it as substrate, And we also change the material type. Go to edit and select FR4. Okay, so we have selected the material here and click OK, apply, and we should also change the color. Let us say it is green in color. Okay, so now you can see that we have created an object and we are not able to see the ground. Let's click on this button, and there are two objects, ground and substrate. Where if we make the substrate invisible, then we are able to see the ground. Let's see both and click, and we can also rotate. We can see that both the objects are there. Now we have to design a patch element. So patch element, for example, we want to create a patch antenna that is resonating at 2.4 gigahertz. Okay, so let's just give the dimension of select a same object. So on top of the conducting material, we are going to use the copper. So let's copy and paste again and rename it to patch. And we select now here this is the height T and this is the height H. So when I want to create another layer here, it will start from T plus H. So I double click here and give it T plus H. Now the patch dimensions are smaller than the ground plane, so I am giving it WP and LP. So WP I am just a guess, I am giving 25 mm. LP I am giving 25. So it is a square patch. And we had H substrate is, and I accidentally write H only. So we have H sub. Then we give this dimension WP and LP. And again, copper has same thickness T. Okay. So now you can see that we have three layers: ground plane, substrate, and our patch. Okay. So I hope you are following till up to this point. Now, for the sake of clarity, let us make all the elements invisible. Okay. Now, again, I am going to start, and this time I am going to create a coaxial cable. For coaxial cable, let us select this cylinder. When I select this cylinder, again we give the center point of that cylinder as reference. Then we select the radius, so has become circle. Then we select the height. Okay. So now we can change this. So first, let us take it, make it center pin, and the material type is copper. Now set the dimensions. So again, we are going to make it variable. For X position, Y position, and Z position. So we are starting with XP, YP, and ZP. The values I am going to give for XP, I am going to give 4 mm. YP, let us give it 0 mm. So there is a trick here. When you are giving the value and you are mentioning the unit. For example, ZP I am going to take as minus 10 mm. So mm is here, and when I click OK, this unit type will automatically be changed. Okay. So the unit type is automatically changing. Now, in cylinders, we have one more parameter, that is number of segments. these segments represent that how many the circular are, how many segments are the circular are composed of how many segments. If we give 0, that means it has infinite amount of segments, so it will give very smooth uh, visual. Okay, but this is this cylinder. And now see if I give it as 3. So you can see that this has become as a triangular rod. Okay, so let's set it at 0 and again select the radius. I want to give it RC1. That will be, we will take as radius 0.55 mm, and height of this I want it to start from ZP. We have selected as -10. So the height will be plus ZP plus. I wanted to touch the upper patch. So at upper patch is at H substrate plus 2 times T. Then click apply. So now we are able to create this and let us fix. Okay. Now we make a duplicate copy of this, and the center pin is of copper. The second copy that we are creating, that we are creating for the shielding the substrate material of coaxial cable. So in that we have usually Teflon material. So select here and select the material and give it as Teflon, and this is your coaxial substrate. Okay. Make the color like this so that you can identify it later. And now change the dimension, so it will be it will have the same center position. So it will we will just changing the radius of this, and let us see, it is RC2, and the value for this we are going to give 1.75 mm. So these values are for the 50 ohm coaxial cable, in which the center pin is of 0.55 mm radius. The coaxial dielectric has 1.75 mm. Click OK, and now you can see it has two materials. And one more thing that I missed, that was when we are creating this substrate, this this coaxial cable substrate, it should not it should only touch the lower ground. So we are it will have only ZP plus T. Right? Okay. I think I made a mistake. It should be minus ZP, and similarly here we are going to give minus Z. Okay. So now we can see both the tables, minus ZP, ZP plus T, and here it is ZP. I think I have rotated this. Let's go to the model and select the isometric view and select on fit off. So here we can see in front view we will be able to clear this there. So right now the value is ZP is minus ZP. Okay, I see the issue. So the variables that we are giving we can go to that by HFSS and design properties. Here we can see that the value of Z is -10, so let us make it positive. Now click on this. So now you can see that the Teflon cylinder is up to this point, and you can see that x-axis is there and z-axis in front view. When we click on z-axis, let us zoom out. So this green is representing a z-axis. So this is our origin point. So the coaxial cable is touching up to 0. Then the center cable is extending there. Now let us create one more cylinder, that is the outer shell. So outer shelling we are going, the outer shell will have copper. So we need to add copper here. Again, change the color of copper. Now it will be exact like the it will have exact dimension as the substrate of the coaxial cable, but it will have uh, increased radius. So the radius RC3 we are giving it as 2 mm. Click OK. Now you can see this is overlapping. So let's get back to bottom view. In bottom view, you can see that there is a cylinder here, one cylinder, two cylinder. But the thing is, all these cylinders are not hollow, and the outer conductor cylinder should be hollow. So for that, what we can do, we can you, first let us rename this outer cell, outer conductor, and we when we select this outer conductor, we see that this is a solid conductor. So what we need to do, we need to subtract this shape from here. So we select the outer conductor, then we select the coaxial substrate, and then we go to draw. And here we have selected only these points. Now we select, these are the Boolean operations that we can use. And let us select this subtract button here. Now, when we are performing Boolean operations, if we are adding both the objects, then there is no problem. But if we are subtracting, then it is important to note down which part we are subtracting from what part. So the blank part, that means from this part we are subtracting, and the tool part is, this is the part that we are going to subtract. Okay. And if we want to keep the tool part there, then you can select this clone tool object. Okay. So from outer conductor, we want to subtract the coaxial cable, and we also want to keep a copy of that. So click on this clone button and then click OK. So now you can see this outer cylinder, it is a hollow. Okay. Now same thing. One more thing that let's go to the top. Now go to the visibility and select the ground. If we make the ground visible, we will find that this area is overlapping. From the left part, this particular area, this area, as the height of the ground is very narrow, so it is not clear here, but that is overlapping. So whenever multiple objects are overlapping and they are of a different when multiple objects are overlapping and they are of different material type, then it will give an error. So for example, we have material changes. From top. So what we can do, we need to, if I select the ground here, this ground is complete. And now if we give the feeding from this coaxial cable, okay, if we are giving the feeding and the ground is there, that means it is short circuited. So what we need to do, we need to make it hollow here. So we need select this ground and then we select this coaxial substrate. Then we again go to subtract and again we want to keep the coaxial substrate here. So click OK. So now you can see we have made a hole in the ground. Okay. Now this coaxial cable is here and this center pin is also here. This is the center pin and this is the coaxial. So both of them are overlapping with each other. So what we need to do, we need to make a cut from this substrate. So we select this and we select the center pin. Click on subtract, clone. So this time what we are doing a coaxial substrate minus the center pin and we are making a clone of that. Okay. So now we have this material and when we see it, you can see this is a hollow material. Similarly, you can see the outer conductor is hollow, the ground has a cut inside and the center pin is there. Okay. Now this is the part up to this point we have successfully created a patch antenna and now we click on visibility and make all the elements visible. Okay. Then we select the ground. So here you can see that this is the top patch element. This is the substrate material and we have a ground plane and that ground plane has a hole here. Then we have designed the center pin of the coaxial cable that is touching up to this point. The center pin is touching the top layer of the copper. Okay. So what else we need to do? Now, once we have developed the geometry, we need to identify, we need to give it some excitation. So for that, we need to select a face to which we will be connecting our connector. So click F button on the keyboard. When you click on F button on the keyboard, it will select only a face, and you can select this by from this select menu. In draw, we have this menu, and we can select what type of object we are going to select. We are going to select an object or face or an edge. So this time we want to select an face. So from here, or we can press the hold key F and select this coaxial cable space. So just to make sure that we select the right object, uh, let's go back to bottom. This is the bottom view and this is the object that we wanted to select. You can either zoom in. Let us zoom this area and select F and we select this dielectric. So here you can see that this is the center pin, this is the dielectric and this is the outer pin. So right click on this and from here we can see that there is an excitation. In excitation we have to assign a port. Okay. So in ports we are going to, okay. One more thing was there that in this when we inserted a design, by default it was a terminal network and this time we are going to implement a model network instead of terminal network. Tomorrow I will tell you why. And let's select this HFSS, select the solution type. In solution type we select this HFSS and there are other solution type, but we are focusing on HFSS. Then it is a network analysis we are performing and we are performing model solution. So in model solution, we get to figure out the characteristic of the model in terms of S parameters and select OK. In model, now we select zoom in and we select this space again. This space we have selected. Now click on right click, then go to assign excitation, then click on port Now you will be able to see the wave port. Okay, so there are four type of ports, and we are going to use wave port here. And when we select the wave port, it asks us the name of the port is port 1, and it is asking to draw an integration line. We select a new line, then from the center to the ground. The outer cylinder of the coaxial cable is ground. So from center we are starting, and up to the outer cylinder we are clicking. So this has defined the modes of this. Then we click next. Here in this we can normalize the results, but we are not going to do that. But this setting de-embed. So this is a post-processing setup, and I will explain you why we are going to use this. And let us give LDEM. Okay, this is the de-embedding. That means we can move the wave port. We can move it inside the feeding line. Okay, so we give this de-embedding, and the value of the embedding is 5 mm for now, and it will appear in the variable, so we don't have to worry about that. Okay, then now we are ready for the simulation, but one thing is missing, that is when we are giving the excitation, the antenna is radiating. So up to what length it is going to radiate, and up to what region the HFSS should consider simulation. Okay, for that we need to define a region. So again, come to draw, and you can see that there are many other type of objects that we will explore later, and these are the 3D objects, these are the 2D objects, and these are lines. Here, one thing is, that is create a region. So region is the extra space that we are adding in our design. So click on region. So it has three options. First, it is pad all directions similarly. That means in all six directions, positive x, positive y, negative plus x plus y plus z minus x minus y and minus z. In all the directions, we are having exact same padding, and the padding type is uh, either we can make it as a percentage of the whole dimension, or we can give absolute padding. So let us give it an absolute padding of 25 mm, or 2.4 gigahertz we are working, so we can give it up to 50 mm. Okay, then click OK. Now if you click on the fit all, so you can see that your whole antenna is this, but the reason is this must be. Okay, now if we select see the hierarchy, then in solids we have some elements that are made up of copper. We have center pin, ground, outer conductor, and page. All these elements are made up of copper. The substrate of the material is made up of FR4. The substrate of the coaxial line is made up of Teflon, and the reason it is made up of vacuum. So we have to assign it as material, and that material will be air. Okay. So air has slight the relative permittivity of air is this. So permittivity is this. So it is very negligible change, but we want to analyze that. So we are selecting it as air. Okay. Now click OK. Okay. So the transparency of this is it is completely transparent. We can see inside out of this, and now we have created the panel also. Now this region right now it does not have any meaning. So in order to give it meaning, what we need to do, we need to assign some boundaries to this region. So select this. Now right now we are selecting, when we select that, all faces are selected. So that means whatever we do, that will be applied to the complete object. So right click here, and there is an option that is called boundaries. So in electromagnetics, we have studied boundary conditions, and if there is a metal and air interface or like that. So most of the time we have studied about the conductors and their impact, but there are other boundaries like the electric conductors that are represented as perfect E. Then there are fictitious magnetic conductor. We represent them as perfect H. And if we have gone through the even odd mode analysis, then you will be able to identify at what position we put the perfect E condition and at what position we put the perfect H. And there are some objects might be there that have some certain impedance characteristic, or they have finite conductivity, or they might have relationship with some other. So those we can simulate, but right now we are going to select their boundary as a radiation boundary. Radiation boundary means that outside this box, at this point, the waves are absorbed. The radiation boundary is nothing but an absorption boundary in which the incoming field that is touching this will be absorbed, and if there is a conductor there, then it that will reflect. So there we are not giving the perfect T, we are giving the radiation boundary. So that will absorb the incoming field, and at this point our gain and other parameters will be observed. So there is like if we change the dimension of the region, then our gain parameters will slightly change. Okay. So now we have given the boundaries. So in here we can see that uh, we have got the boundaries. So these are the boundaries. Then we have given a excitation. That excitation was there, and if we click on fit selected, then it is showing this is your excitation. Okay. Now there might be some slight errors that we might have forgotten, but let us start with simulation and I check it. Okay, so first we need to select the validate the design. Okay, so for whatever steps we have done, we have to check if those steps are right or wrong. So this model, we need to validate this model. So when we click on the model, then it is displaying some errors. So the first error, that is 3D model error. Then we have boundary and excitation error. Then we have setup error. So let us handle one by one. So if you see in the message center, we see that part ground and outer conductor intersect. Okay, so let's go to this, and this is our ground, and this is our outer conductor. So both are intersecting. So what we can do, uh, we see why it is intersecting. It is starting from -10 and it is extending up to ZP plus T. Okay, so if we remove this plus T from here, we will be able to see remove this particular error. Then part patch and center pin intersect. So the center pin, it is extending up to, it is starting from -10 and extending up to 11. So it is 1.538. So this 2T, we need to change it to H sub plus T. Okay. So now we have removed both the ports. Then again, let us clear this, right click and clear message for port 2. Again validate. Now we have part of the substrate and center pin are intersecting. Okay. So this is the substrate and this is the center pin. So we need to remove this and go to here. From substrate, we are subtracting the center pin and clone of the center pin. Okay. So right here. Hopefully this time the modeling error will be resolved. Okay. So we have resolved the modeling errors. Now the error is 3D boundary condition. Okay. So what happens when we have the excitation? The excitation uh, in when we are applying a wave port, then wave port must uh, touch the boundary condition. So we have this region, and if we see, the region is like this. So our wave port is placed at this position, whereas our region is extending up to this point. So what we can do, we can go to region, select it here, then double click, and in -z we put 0. Okay, so now it is touching there. Again, go to the simulation and validate the design. So that error has been resolved. Now one more error, that is analysis. We need to define a solution setup. I said that we are ready for the simulation, but at what frequency we are going to uh, simulate. As for that, here we select this analysis and right click on this and add a setup. We are going to use the advanced setup, not the auto setup. In advanced setup, we have three options. We have an adaptive solution at a single frequency or a broadband frequency. I am giving a broadband frequency and I want to design the antenna at 2.4 gigahertz. So I am giving 2 gigahertz to 3 gigahertz. Okay. And then these are the number of passes that I am going to explain you. So if you are able to see, here there is a circle. Let us start with a simple square. So what happens in simulations, we solve the Maxwell's equations, and those Maxwell equations we are not solving at infinite amount of time. We are selecting certain points on which we are going to solve those problems. For example, right now in this circle square we see 1, 2, 3, 4. At these 4 points we are going to select this equation. Okay, then that will give very ambiguous results, because what happens in between these points we are wrong. Then what happens, we can increase the number of points by drawing two more lines like this. Now we have 1, 2, 3, 1, 2, 3, total 9 points to calculate the fields. Again, if we refine, that means we increase the number of points. So like this. So here we are able to see more number of points. Again refine. So like this, we can increase the number of points. And let us reset this. Now you can see that there is a convergence plot. At first point, when I increase the number of cells, number of mesh, it it has nothing there. But again, when I increase, it is displaying a graph. Okay, so between two consecutive points, it is displaying the change in the uh, results. So that results that can be identified as the S parameters or the electromagnetic energy inside the structure. So as we increase the number of refinements, you can see that that difference is decreasing. Okay. So that is the principle that is used inside this HFSS. So it will be calculating the parameters at the center frequency, that will be around 2.4 or 2.5 gigahertz. And it is targeting that between two consecutive passes, we have a maximum of 0.02 dB variation in the S parameters, and maximum number of passes we are setting as 6 passes. Okay. For higher accuracy, you can increase the number of passes, and we click on OK. Then once we click on the that has selected a wide frequency range, so we need to define a sweep there, that from what frequency range we are going. So the start frequency we are giving as 2 gigahertz and frequency is 3 gigahertz, and the default number of points are 401. That will be very high, so we change it as 400 and 101. Okay, now this sweep has three different types. So a discrete sweep, interpolation, and fast. So we are for this simulation we are going to use the fast sweep. We if you want better accuracy, you can go for discrete or interpolation, but that depends on your hardware, how much RAM do you have, and how much time it will take. So we are selecting the fast sweep, and we are saving the 3D fields, and there is an option to save only the radiation field instead of the complete electric and magnetic fields. That will reduce the size of the your file. So right now we are selecting all the fields. Click OK, and then now when we validate, everything is perfect. And it is one more thing is there, that it is radiation. So click on this radiation, right click, insert far field, and give an infinite sphere in which phi is varying -80 to 180, theta is varying 0 to 30 to 180, and in steps of 2, that will be varying in steps of 10 degrees. Okay, so it will create a sphere around the model, and at the points of that sphere we will be calculating the electromagnetic field, and from that we will be calculating the gain and other parameters. So now everything is set up. Now click on the analyze call. So for that I need to save this, and save this file as project 2. Now it is running, and at the same point you can click on this result, and you can click on the solution data. Okay, in solution data there is a profile and convergence. So we have maximum number of 6 passes, and we are setting the maximum magnitude delta, that is 0.0602. So what happens that suppose after 2 or 3 passes the variation in the S parameter is below this target, then the setup will stop. So the first pass is completed, and there is no make delta S because it is the first pass. Now the second pass is completed, the magnitude difference is 0.08, and so still the program is not converged. In third pass the program is about to converge, but no. So 3 passes have completed. Let's see in fourth pass. In fourth pass the outcome is like this. So the setup has converged. So we can also see the plot like this. So this was the limit, and we have reached this. After 4 passes, we have stopped because the delta S is less than 0.002, zero 0.0. Okay. Now, if you see the profile here, you see that when the simulation started, the initial meshing was 33 mm. It was consuming only 33 megabytes of your RAM. In the last pass, after 4 passes, you see the memory is 600 megabytes. That means 10 times of the first pass. So if you want higher accuracy and you set this up to very high value, this target value is very low value, then the number of passes will increase, and you will also increase the number of passes. Then at certain point it is possible that your simulation setup is not converged, but your system has gone out of range. So be careful about the size of your data. Okay, then now the simulation it is showing that normal completion of simulation. Okay, so now we have completed the simulation, but where are the results? So in results, there is nothing. So actually we need to create the reports. So right click here and create a model solution data report, create a rectangular plot. So in that we can select the S parameter, and we have only one port, so we are only able to see S11. Then there are other parameters like we want to display S11 in dB, or we want to normalize them to 10 dB or 20 dB. So let's go with the default setup. Okay. So now, as we have not calculated the exact dimension, so it is giving us simulation up to this point. Okay. Now again right click here and select a rectangular plot. This time we are going to use Z11 and we are not going to use dB parameters. We are going to use real and imaginary parts. Okay. So real and imaginary. So you can see uh, we can overlap, we can either modify this report and real and imaginary. We can add the traces and in those traces we can give it as y2. So from here we can see S11. From here we can see real part of Z11 and imaginary part of Z1. So you can see that the S parameter dip is here. The real part of the impedance is maximum at this point, and the imaginary part of the impedance is not touching the zero. So that means we need to optimize our design to so that the imaginary part is maximum or it is matching to 50 ohm, and the the real part is 50 ohm, imaginary part is 0, and we have S11 dip there. Okay, so I have created some simulations earlier, and let us save this first. Now let us save this design, and let me show you the designs that I have stored earlier. Open, click open, and this is the design that I have created earlier. So we are using a coaxial feeding. In coaxial feeding, these parameters are like this. So I have optimized the design. That means I have optimized the parameters of the design, and you can see the Z parameter. The real part is about 47 ohm, and at that point we have very less value of this imaginary part. So from this project, from these results, what we can conclude that when we are going to define the frequency, we can right click here and add some markers. Let us add a Y marker, and that Y marker is on, we are placing it on -10. So in the S11, the parameter is the S parameter is below 10 dB at 2.694 gigahertz to 2.738. This is your impedance bandwidth, and you can see in this range the impedance is below 50 dB, and the imaginary part that is like this. So this S parameter is a combination depending on the input results. So you might see that the imaginary part is not even touching the zero, but since the real part is very close to 50 ohm, therefore we are getting this matching. Okay, so in order to improve the matching, what you can do, you can change the position of the feeding. So we have given the position as a variable. Remove this and select fit all. So this is the position. So we can shift this without changing the physical. Like if I click here and make some changes and then click OK, then my current results will be deleted. Okay, so that is why we have already taken care that we can change the dimension without going to this window. So what we can do, we can select this, click at this position, we select this design, then all the parameters that are that we have defined, or the variables that we have defined, we can identify those variables. Okay, now this de-embedding, this is when I click here and see the design properties, So all the parameters that all the variables that we have declared, all these variables are of type design type. But this LD embed, that is a post-processing variable. So if we change any of these parameters, that will change the physical structure and all results will be discarded. But if I change this LD embedding, that is a post-processing variable, that will not discard your results. Okay. And why do we use this? Let me show you. For example, this is a patch antenna that is fed by insect feeding. And in this, I have applied this de-embedding. And okay, so here you can see, I think I have to re-verify that. Okay, tomorrow I will give that demonstration. So here we have selected this S parameter and we have selected the Z parameters. And now we need to see the field report. So you select here, click a field report here as a rectangular flow and right click, click a, create a far field report because the antenna parameters like gain, efficiency, those are parameters at the far field. So we select the create a far field report, then click on the variable, then we click gain total and the unit of that will be dB. Now, uh, uh, from which simulation we are going to extract get the solution. So we have a setup that is last adaptive setup, and we have a sweep. Last adaptive setup, that is when we are that is when we are selecting the mesh size. Then we once the mesh size is completed, this that was done on a single frequency, that was 2.5 gigahertz as center frequency. Then we have a sweep. So first let us draw this at the last adaptive. So in last adaptive, then we have this so many figures, so many diagrams, and we are seeing the result at frequency 2.5 gigahertz, phase angle minus 180, minus 170, all those phases. All those for all those cuts, we are able to see the results here. Then I want to see the results at this. How our antenna is radiating at this point, 2.7 gigahertz. I want to see the result at that point. So if I go to this report and click on families, now I want to select the frequency. I am not able to select any frequency because this last adaptive has only one frequency. So let us select this sweep, and then I will be able to change the frequency. Okay. So now we can change the frequency, then apply. So here we are able to see that the maximum gain is about 2.5 dB, and this is showing a different results. Now right click here, and another thing is create antenna parameters. So antenna parameters will not show this many graph. It will give us antenna parameters like the peak directivity, peak gain, peak radiation, realized gain. These are the things that we can identify. So let us draw this peak gain and peak realized gain in dB, and we are going to use the sweep and click next. So what will happen that if you can imagine the 3D sphere. In the 3D sphere, we have pi minus 180 minus 170, these 36 parameters, and for theta there are 18. So all for all those points, it is calculating the gain and identifying the maximum out of those points, and that will be displayed here. And in addition to that, if you want to create a far field report and a 3D polar flow, you can also draw that. Okay, so let us wait for this to complete. think I have made too many points. So whenever you are saving the fields and you want to draw a frequency versus gain chart, then you need to make sure that there are sufficient points for a smooth graph, but it does not exceed, because for every frequency you will have to, the software will have calculate. So if you see here, currently it is calculating for 2.44 gigahertz, and it has to calculate up to 3 gigahertz. Okay, so at each frequency point it is calculating and it is moving in that same way. Now, as we have all set only 101 points, that at that time we are getting this many. What if we assume if we have taken 1000 elements, then how much time it will take? So that all depends on your requirement, how you want to analyze the system. Let us wait for 5 minutes. Now, if we close, then we are able to see that this is the peak realized gain, and this peak realized gain, and let's copy this, copy data. Okay. So the peak realized gain at this point is around 2 dB, and you see the peak gain. Peak gain is way better than the realized gain. So whenever you are reporting your results for the gain, you have to mention the peak realized gain, because the peak gain does not consider the effects of losses, and that does not consider the effect of your efficiency. So this realized gain, this is the actual gain that you will be able to measure in your setups. And uh, this is the result. And now let us go far field report and create a 3D polar plot. And we are going to use the sweep and select the frequency as 2.7. CSC department. हमारे okay. So now you see we are plotting gain, and the total gain we were plotting. We have not selected this, so let us apply this dB. When we apply trace, so this is the kind of let us rotate this. This is the radiation pattern in 3D, and we can also create radiation pattern in results. We can also create the same radiation pattern in 2D and select the x-axis. In rectangular plot, we can use select the sweep. And, 2.7 gigahertz. And for we will be selecting it for phi equal to 0 and phi equal to 90. In these two planes, we are going to draw this. So this is how the field is moving. We can also create when we right click, we create and we can create radiation pattern that we use to see in the box. Okay. So now, right now, we are not able to. We are only able to see the half part of this radiation pattern because we in the definition of our radiation pattern, we have selected theta from 0 to 180. If we select it from minus 180 to 180, then we will have this will update from the results and we are able to see this. Okay. And if you want to draw here the uh, you want to draw the co and cross polarization, you can do that. Okay. So here we are able to see that this is giving a highly linear polarization because the cross polarization levels are way beyond this. It is 2 dB and this one is minus 38. So it is way beyond the required polarization, cross polarization level. So our antenna is giving highly resonant. So what we need to do now, we need to optimize the dimensions of this patch. So we need to optimize this WP and LP, and we need to optimize XP. These three we have to change and analyze the results. And we need to make sure that the S parameter is has a is below 10 dB at 2.4 gigahertz. The peak is at 2.4 gigahertz. Then we can say that we have designed the antenna. I think we have around 540. Any questions? If anybody have any question so far?
Participants, you can please ask the questions if you have any query.
Okay. Okay, Swati, you can please collect the query. I am giving coming in 5 minutes.
Okay, okay, sir.
Okay. Okay, so Afrin is asking how can we identify the polarization from radiation pattern? How much time? Okay. So the polarization that depends on the shape and alignment of your antenna. And right now we have only created a simple microstrip patch antenna that is a linear polarization. From the here from this graph, if you see, there are different type of gains. We have a total gain, then we have phi, theta, x, gain x, y, z. So if currently we have aligned our antenna in x and y plane, so it is z polarized. Okay, and if our antenna was a circular polarization, then we might have seen the LFCP or RSCP radiation. And with that, what we can do, we can check for the Excel ratio. Excel ratio gives us, if the value of Excel ratio is below 3 dB, then we can say that our antenna is circular polarized. For linear polarized, it is highly recommended to have very high Excel ratio. If it is more than 40 dB, that is highly highly linear polarized. If it is above 20 dB, then it is linear polarized. In between, we have elliptical polarization between 3 dB to 10 dB. That is a elliptical polarization. So we can draw the from this plot where we have plotted these antenna parameters. At this point, we might have plotted this Excel ratio also. Okay. Right. If you create a report and antenna parameters report. Let's say this is your direction. So you can see that the peak rate direction of radiation is theta 0 and phi 0. So we click here and click on the far field, create a report in uh, give me 5 minutes. Okay, so we go to the report and select Excel ratio, then plot the Excel ratio in dB. Now select the sweep and we are going to plot this Excel ratio versus frequency plot here. So we select in the primary sweep as frequency, then go to families and select theta is 0, phi is 0. Why we are selecting this 0? Because the direction of maximum radiation is 0. From the 3D plot, we see the direction of maximum radiation is 0. So we are selecting it, we are calculating the Excel ratio in 0, 0 direction. And with respect to frequency, we are calculating. Then create a new report. So you see the Excel ratio is above 37 dB at all frequency points. That means it is highly linear polarization. Then when we are plotting the co and cross polarization, so that is we can also identify from there that we have the core polarization and cross polarization, they have very huge separation gap. Okay, and so we are able to say that the antenna is linearly polarized from Excel ratio. If it was less than 3 dB, then we could say that it is a linearly polarized. At that point, we have to calculate the LSCP and RSCP plot. Then we identify whether it is a left-handed circular polarized or right-handed circular polarized. Okay, and I hope Afrin, I got it, your queries resolved. Dr. Ramesh, how much time required to understand this HFSS tool? That all depends on the time and practice you give. I think if you give 1 hour daily, then within 6 to 7 months, you might be able to have a better understanding. But you need to practice on different tools. It is not like you are just doing the same thing again and again. And is it possible to design MIMO antenna? Yes, we can. We will be working on MIMO antenna in this software. In next sessions, we will be working. Can we design any type of antenna? Yes, most of we can design. If you can create a model of that antenna, you can simulate it inside the software, inside HFSS. Okay, it all depends on your creativity. For example, I have created this simple microstrip patch antenna with simple rectangles, and I did selected a particular methodology. You can create your own methodology. What you point out, design it. Yes, for millimeter waves, it is possible, and we will also design an antenna for SIW at 28 gigahertz. We will be designing an antenna in next sessions. Is it better than CST or both are same? Okay, so that is a very tricky question because CST works on a different principle and HFS work on different principle. Both of these softwares are 3D simulation softwares, and both are fully 3D. And CST works on finite time domain difference, whereas HFS work on finite element method. So both the methods are different for analysis of the problem, but the results they are very close to each other. Okay, so if you have the right simulation, then both of your results will match. A maximum 5% of variation will be there. If uh, there is more than that, the difference is more than 5%, then you should analyze. You might have done something wrong in any of the design. Okay. For biocompatibility, what we can do, we can develop some models, and we need to determine the properties of bio those models. For example, we can have a vortex model of the head, and we can analyze the antenna impact, and we determine the SAR values using this. Okay, but that will require a lot of memory in terms of RAM and size. Okay, so tomorrow I will also describe you a little bit more about how this meshing is impacting. So if you see in this results, the solution report, I have already shown you the profile. In the first pass, the memory was around 29, 100, 200 MB. That was the maximum. And in the last, we are going up to 600. So the size of your model and the frequency at which you are operating, that affects your calculation size. Okay, but definitely you can do this, and I think this student version limits you with the calculation. So a biocompatible, you can have a academic license in your institute, and in that you can calculate the SAR, etc. Any more questions?
Thank you very much, sir. Sir, undoubtedly, this session was very much informative, and surely our participants are able to understand the HFSS from the scratch. And if the participants have any more query, you can drop in the chat box. We can ask tomorrow also. Thank you very much, sir.
Okay, thank you very much, ma'am. And that was a great session. That was very nice experience with such in, uh, intuitive students. I will be happy to share tomorrow also. And if you have any, okay, what is the cost of HFSS academic license? You might need to contact the vendors. I can give you the vendors number tomorrow. Okay. Okay. Uh,
Thank you, sir.
okay.
We
Thank you very
can, I
much.
think, end
Uh,
today's session.
let's hope we see you tomorrow. Okay.
Okay, sir.
Should I close now?
Yes, sir. Yes. Dear participants, tomorrow the session is going to start from 9:30. You are required to please join at least half an hour before. If you have any issue, yes, Rahul sir, yes, if you have Canvas issue also, we'll work on that. And soon we will solve your Canvas issue. Thank you very much, sir. Thank you.